what we're doing this afternoon are the supplementary topics 2 and 3. And it's a little bit more about gases, and I want to look at the relationship between volume, pressure, and temperature of gases. I want to introduce partial pressures, which is associated with what happens when you've got a mixture of gases, and briefly look at the solubility of gases, and this has implications in a biological context. And then move on to looking at energy changes in reactions, and we'll find that the energy we normally talk about is something we call enthalpy, and look at reactions which give out energy, reactions that take in energy, and finally look at something we call activation energy, which is the energy needed to get things to occur. But first, there's a quick demo I want to show you that I forgot to show you this morning, which really sort of demonstrates surface tension. So I've got water. Water actually has really quite a lot of surface tension because the attraction between the water molecules is relatively strong. That is relative on a non-bonding sense, relative in terms of the intermolecular attractions. And we've seen this for some insects that they can kind of skate on top of the water. If I take a fine powder, and let's just take some sulfur powder, I can scatter it, oh, it's not much, is it? I can scatter it on top of the water, and the surface tension keeps it there. The surface tension is easily sufficient to form this sort of skin on the water that supports some weight, not a huge amount of weight, but some weight. And then if I add, say, a little bit of detergent, this disrupts the surface tension, and once I disrupt the surface tension, then what we'll find is that the sulfur then sinks, being more dense than water. So a quick sort of simple demonstration of what surface tension can do. But a little bit more on gases now, and the behaviour of gases under different conditions. A lot of work was done on this area early on, and the English chemist Boyle was one of the early pioneers. And Boyle found that there was an inverse relationship between volume and pressure, so that if you double the pressure on a gas, you halve the volume. Simple as that. And I might graph that in terms of volume versus pressure. If I have a high pressure, I have a small volume. If I have a low pressure, I have a large volume. And what he found was that pressure times volume is a constant. And I could write that pressure times volume is a constant, something like that. And what that means is that if we know let's say, the volume of a gas under certain pressure conditions, we can calculate the volume of the gas under different pressure conditions. Because pressure times volume is always a constant, then if I say have 1 litre of gas at 1 atmospheric pressure, and I want to know how much space that gas takes up under perhaps 5 atmospheres of pressure, then I can use this relationship where the starting pressure volume equals the final pressure volume. If I have 1 litre at 1 atmosphere, then I'll have 0.2 of a litre at 5 atmospheres, because pressure times volume is always constant. And I can imagine this in terms of the kinetic molecular theory of matter, that if I, for example, have a certain number of gas molecules in a space, if I reduce that space, reduce the volume, I crush them into a smaller volume, they're then moving around, they are more frequently hitting the sides of the vessel, or that there are more frequent collisions with the sides of the vessel containing the gas, and that manifests itself as an increase in pressure. Now, the other one of the other players in this was someone called Charles, a Frenchman. That was his surname. And what Charles found out was that temperature and volume were related to one another. And if I take, for example, my balloon, and I can see that actually I haven't really done my size calculation very carefully here. And what I want to do is try and cool down the gas in the balloon, and I'm going to use some liquid nitrogen to do that. So if I pour my liquid nitrogen over my balloon, cooling down the gas far enough so I can actually get the balloon into the container that I designed it for. This is quite an extreme form of cooling, of course. But what I think you can see is that volume decreases as the temperature decreases. And this is reversible. So if I increase the temperature by removing the balloon from the cold, the gas will expand. And actually, I don't know whether you might be able to just see that there's a liquid at the bottom in the balloon. That's actually liquid oxygen, because at liquid nitrogen temperature, then oxygen condenses out of the atmosphere. So we've actually liquefied the oxygen in there, and that of course will make an even greater difference in the volume. But we've also reduced the size of the balloon quite a lot. Now that is a reversible process, so if I leave my balloon to warm up, I hope it will attain the original size. And I can sort of graph this in terms of volume versus temperature. So the higher the temperature, the bigger the volume. And the lower the temperature, the smaller the volume. And what we find is that actually for a number of gases, I find that I can get a straight line relationship which I can extrapolate back to what we set as our absolute zero of temperature. Now we can never actually attain our absolute zero of temperature, but you can imagine the situation that in a gas we assume that there's a lot of empty space, and we also assume in a lot of our theories of gases that the particles associated with the gas molecules or gas atoms take up no size, and that's not quite true. It doesn't matter so much when we have a gas, say at room pressure and temperature, but when you get to a very cold gas, then the size of the particles actually does become significant. But what we can do is extrapolate our volume temperature line back to an absolute zero in temperature. And that absolute zero sets what we call the Kelvin temperature scale. So if I measure temperature in terms of Kelvin, then the absolute zero starts there and we go upwards. If I measure temperature in terms of degrees C, and maybe I should just color code this, I know that 0 degrees C and 100 degrees C perhaps corresponds to this part of the graph. We find that on the Kelvin temperature scale, a degree Kelvin is the same magnitude of size as a degree centigrade. The difference is that absolute zero on a centigrade scale is minus 273 degrees C. Well, that means that on the Kelvin scale, where we're starting at zero, freezing point of water is then going to be plus 273 Kelvin, and the boiling point of water is then going to be plus 373 Kelvin. And that a warm summer's day, 25 degrees C, 298 Kelvin is taken as a sort of a standard temperature. So what we find is that volume and temperature are directly related by a constant, and I could write that as, bless you, volume equals constant times temperature. I could rearrange this and say, okay, maybe we could express it as volume over temperature under conditions 1 equals volume divided by temperature under conditions 2. The thing to remember is that the temperature is always expressed in Kelvin. And that way we get around the problem of potentially, let's say, dividing by 0 if we want to look at something at the freezing point of water. So temperature's always expressed in Kelvin. And I can imagine sort of what is going on. As I reduce the temperature, then I slow down the motion of the particles. And if, as in with my balloon, I have the balloon as a flexible volume at atmospheric pressure, if I slow down the movement of the particles, they will be hitting the sides, the inside of the balloon, with less force and less often than when the gas is at room temperature. That translates to a reduced pressure. And as a result of that, the constant 1 atmospheric pressure outside then tends to reduce the volume of the balloon, and we end up with a smaller size. In terms of units then, temperature is always units of Kelvin. Volume, well, we usually use units of litres, but to be strictly correct, we should use units of cubic meters. Pressure has a range of units that are used, and for example, depending on the age of the textbook, we can use units of atmospheres, where standard pressure at sea level is 1 atmosphere pressure. We can use units of millimeters of mercury, which relate to measurement of the pressure using a manometer, and 1 atmosphere is 760 millimeters of mercury. Or we can use kilopascals, which is now the preferred unit of pressure, and 1 atmosphere is 101.2 kilopascals. So how can we really combine these? We see that pressure volume equals a constant, volume is a constant times temperature, and if we look at a situation where we have a single, say 1 mole of a gas, we can combine these laws, Boyle and Charles's law, into what we call the ideal gas equation. And the ideal gas equation, the ideal bit doesn't mean to say that it's, it's a really, really good equation, but it is. The ideal bit says that we're making some assumptions about the gas, that it acts as an ideal material in which there's no interaction between the gas molecules, and that the gas molecules themselves don't have any size associated with them. And those approximations are pretty good for everything we want to do, pretty much everything we want to do. And the ideal gas equation is pressure times volume equals numbers of moles, that had to come up somewhere, times the universal gas constant times temperature. So we're sort of combining PV equals some sort of combined constant times temperature, and we're adjusting it for numbers of moles. The value of R depends on the value of units you use for things like pressure, whether it's atmospheres or kilopascals. But what this enables us to do is determine an unknown quantity given a known amount of gas at a particular temperature and particular pressure. For example, we can determine volume, or we can determine pressure given volume, temperature, and number of moles, that sort of thing. And very often when we're looking at gases, we have a particular amount trapped in a bit of apparatus, a balloon, something like that. We know a certain set of starting conditions. We want to know a set of finishing conditions. And pretty much like the pressure, volume, temperature equations there, I can say that pressure, volume over temperature under conditions 1 always equals pressure, volume over temperature for conditions 2 for a given amount of gas in a container. So I can relate these things together, and that can be particularly useful. Okay, so that's really good when we've got a pure gas. We next have to think of how do we deal with a mixture of gases such as the gases in the atmosphere. We know that the atmosphere is about 80% nitrogen, 20% oxygen. And what we use is a concept called partial pressure. And partial pressure is the pressure exerted by an individual gas if it was in that container on its own. Now, imagine a situation, imagine a balloon with ordinary air in it, 80% nitrogen, 20% oxygen. We say that the partial pressure of, say, nitrogen is equal to 0.8 of an atmosphere. It's as if we had just the nitrogen there in the balloon, it would exert a pressure of 0.8 of an atmosphere on a day like this. If we had just oxygen present in the balloon, it would exert a pressure of 0.2 of an atmosphere, because we've got an 80%, 20% split between nitrogen and oxygen. So the partial pressure of a gas is the contribution that gas makes towards the total pressure, and as a consequence, the total pressure is the partial pressure of the component parts. So, for example, if we look at, say, air at 1 atmosphere, then the total pressure of air equals the partial pressure of the nitrogen present plus the partial pressure of the oxygen present, and we won't worry about the very small amount of carbon dioxide, argon and other things. And I know from analysis that the proportion of air that is nitrogen is 80%. So the partial pressure of nitrogen, we say, is 0.8 atmospheres, and the partial pressure of oxygen is 0.2 atmospheres, corresponding to the 20% that is the oxygen present. Okay, so we've got a way of dealing with mixtures of gases. Now, the sort of next stage in this is to have a look at what happens to a gas, let's say oxygen, when, for example, it dissolves in water, and solubility of gases, and how that is affected by the type of gas. And really the solubility of gases depends on three things. It depends on the nature of the gas, and some gases will interact. Disconcerting creaking sounds there. I'll just put that back in there. If a gas interacts with water to a large extent, then it's likely to be very soluble in the water. So, for example, if I take HCl gas and dissolve it in water, then it actually forms hydrochloric acid. It splits up 100% into H plus and Cl minus, and so it is very, very soluble in water. And that's a bit of an unusual situation. More often, we're looking at a gas that doesn't react with water, as HCl does, but we're just looking at the solubility of a gas in water. And if it's something like oxygen, then clearly this is really important for aquatic life, the solubility of oxygen in water. So, three things affect the solubility: the nature of the gas, the pressure of the gas, and we find that the higher the pressure, the more soluble the gas is. And we can imagine this if you think of water in a closed container. You increase the pressure, you consequently bombard the surface of the water with more gas molecules and more gas particles, and they're more likely to then dissolve. We can see the effect of this in things like carbonated drinks, where you bottle your lemon orange crush or something like that. You bottle that at 4 atmospheres of carbon dioxide pressure, and then when you open the bottle, you get a fizz, and the reduced pressure means that the CO2 dissolved in the water then bubbles out of solution. And this actually becomes significant if, for example, you're a diver. When you are down at, let's say, 30 meters, the pressure is at least double that of atmospheric pressure. And as a consequence, the gases that you're breathing are much more soluble in your blood than they would be at sea level. If, for a moment, you imagine you're breathing a standard mixture of 80% nitrogen, 20% oxygen, if you double the pressure you're under by diving, then you'll double the amount of those gases dissolved in your bloodstream. If you then come to the surface very quickly, you get the same effect as opening the top on a bottle of fizzy drink. The gases are quickly released from the bloodstream. They don't have time to go through the blood-air barrier that's in your lungs. Now, with things like oxygen and carbon dioxide, there is a metabolic way of adjusting those gases in your bloodstream, so they're relatively easy to get out of the bloodstream quickly. But in terms of nitrogen, there isn't. And if a diver comes up to the surface too quickly, then they get the nitrogen bubbling out into their bloodstream. It causes tiny bubbles, particularly accumulating around the joints, and that can be extremely painful and can even lead to death in some circumstances. What people in extreme deep sea diving situations do is often breathe a mixture of gases which has less nitrogen in it and more gases like helium, because helium doesn't dissolve in water or in blood to the same extent that nitrogen does. So it's back to the nature of the gas. And as a consequence, you have less in your bloodstream when you go down, and less in your bloodstream to be removed from your bloodstream when you're decompressing as well. So, increased pressure, you increase the solubility of the gas in the bloodstream. The third aspect is temperature. And if you increase the temperature, you decrease the solubility of the gas in water. And that actually seems a little bit strange, because most of us, our experience of solubility is things like dissolving sugar in water, salt or whatever. And we know that for most solids, if you dissolve them in water, then increased temperature increases the solubility. It's easier to dissolve something in hot water than in cold water. But in the case of gases, an increase in temperature decreases the solubility. And the reason being that if I consider this reaction, as I increase the temperature, I provide the oxygen molecules that are dissolved in the liquid with more energy. And if the more energy they have, the greater the chance they have to escape from the liquid back into the atmosphere. So on a hot day, then you will get nitrogen bubbling out of a glass of water as it warms up from reservoir temperature up towards room temperature, something like that. So, three things are important in the solubility of gases. Okay, so what I want to do is leave gases for a moment and move a little bit further on to heat change and looking at heat changes in reactions. We've seen in this section how heat, in terms of temperature, can affect the physical properties of materials such as gases in terms of pressure, in terms of changing volume, in terms of solubility, things like that. In most cases, chemical reactions involve some sort of heat change. And we first have to ask the question, why is that? And if we do a simple chemical reaction, such as reacting hydrogen with oxygen, and I'm going to write it out in this fashion to emphasize the fact that what we're doing in a chemical reaction is changing the bonds present. And we're breaking, for example, a couple of hydrogen-hydrogen bonds, an oxygen-oxygen bond. We're making a bunch of hydrogen-oxygen bonds. And bonds of different sorts have different stabilities. And as a consequence of that, when I change the sorts of bonds present between the atoms, I'm going to change the stability of the molecule. And in some cases, I will produce a more stable molecule, and when I produce a more stable molecule, heat is given out. And in other cases, I might take in heat in order to produce a less stable situation. And we have a couple of names for this. For a start, the heat we deal with is something called enthalpy. And enthalpy can be either given out in a reaction, and in that case, we say that the reaction is exothermic. Which is literally, outside heat. Heat's given out. If, on the other hand, enthalpy is taken in, we call that reaction an endothermic one. Now let me show you. Let's start by showing you an endothermic reaction. And what I'm going to do, it's sort of a little bit difficult to show easily. So I've wetted that board. That's actually frozen to the bench, and that's just what I want to do. Now, I want to mix two materials together. This is sort of a little bit of an unusual reaction in that it's a solid state reaction. It occurs with solids. Barium hydroxide, and actually let's put that in there first and add my other solid to it, and then I'll mix them together. There's probably a quicker way of doing this. Let's just reactions don't normally occur between solids, and in part that's because of a mixing problem. It's usually difficult to mix solids sufficiently to get a reaction to occur. So what I'm going to do is mix those up. What I find is as the reaction occurs, heat is taken in from the surroundings. It's an endothermic reaction. If heat is taken in from the surroundings to power the reaction, then the surroundings get cold, and I can feel that the flask is getting a little bit cold. So I'll leave it for a moment, and we'll see what happens as the reaction proceeds. But just a quick story. I remember when I was a kid going to the dentist, and you know, they're not pleasant places to visit, and the dentist, trying to encourage me, gave me a tiny little bit of gold leaf and put it in a tube, and in the other side of the tube, with a bit of cotton wool between the two, he gave me a tiny bit of the mercury amalgam that they used to use for fillings in those days, and he told me never to let them touch. And of course, as soon as I got home, what did I do? I touched them, and there was an instantaneous solid state reaction in which the mercury atoms diffused from the amalgam tooth filling into the gold. And what I saw was the gold went from a nice yellow colour to grey. What I did, of course, was burst into tears. But what you should always bear in mind, that if you ever have, say, a mercury thermometer, and you don't come across them so often now, and break it, then if you have any gold jewellery on and the mercury touches the gold, it'll instantly, the mercury atoms will instantly diffuse into the gold, and you'll end up with something that looks just grey, which is, you know, not as attractive in colour. Okay, so what we have now is that the reaction's taken in heat from the surroundings. A consequence of that is that it's cooled down the moisture around the bottom of the beaker, and I've frozen the flask to the wood. So that's an endothermic reaction, and I'll show you an exothermic reaction in a few moments that I've got in the fume cupboard. But a couple more bits of terminology here. Enthalpy, we can measure it in terms of things like temperature change. We give it the symbol of H. And what we find is that it's very difficult to measure the absolute quantity. It was impossible, in fact, to measure the absolute quantity of enthalpy in a material, because the complexity of the interactions between the energy stored in a material resulting from proton-electron attraction, resulting from electron-electron repulsion, resulting from the bond between atoms, all those sort of things. What we can do, however, is measure change in enthalpy. And that's normally what we're interested in. If I'm using hydrogen as a fuel, I'm interested in how much energy is given out as the hydrogen burns to give water, in this case. So it's change in enthalpy, which we indicate by a capital delta, delta H, which is what is important here. And we find that if the reaction is exothermic, our convention is that we assign a magnitude to it and give it a negative sign. So that tells me that energy is given out if the value for delta H is negative. Conversely, if enthalpy is taken in, if a reaction like that demonstration absorbs energy from the surroundings, then we can write out the reaction in a balanced chemical equation. We have a value of delta H, which we can then indicate as positive in a thermodynamic equation to actually indicate the energy change that's going on. So that, for example, let's say I burn carbon in oxygen to give carbon dioxide. I can measure the amount of heat that's given out in that reaction by looking at the temperature change of, say, a jug of water being heated in this way, perhaps something like that. And what I find is that delta H is minus 394 kilojoules per mole. Now, we're not so concerned with the actual value. What I want to point out is a negative sign there is our convention for saying energy is given out in this reaction. Our units are in terms of kilojoules per mole, and all that means is that when we're measuring enthalpy, we're measuring it on a molar scale. The actual amount of heat depends on how much of the material we have. And if I was to write this equation, for example, 2 lots of carbon plus 2 lots of oxygen giving 2 lots of carbon dioxide, then in this case the delta H is going to be twice this value. And similarly, if I reverse this equation, then heat is no longer given out, but heat will be taken in, so that if by some means I start with carbon dioxide and break it up to produce carbon and oxygen gas, then heat has to be taken in order to do this, because carbon and oxygen gas is less stable than carbon dioxide. So this is an endothermic reaction where delta H is plus 788 kilojoules per mole in this case. So we always need to associate a value for delta H with an equation so that we know whether heat is being given out or whether heat is being taken in. And before I show you the final exothermic reaction, I also want to mention that in some of the demonstrations I've shown you, we've clearly had an exothermic situation, sodium burning in chlorine, for example, or hydrogen and oxygen burning together, because we get heat, we get light given out. But in most of the cases, I've had to do something to start it going. In the case of sodium and chlorine, I've had to add a drop of water just to start it going, or strike a match, or something like that, to initiate the reaction. And very commonly, you find that reactions need a little bit of a push to start them going, and then once they start going, they can sustain themselves. And I can portray this in an energy level diagram. And let's imagine this diagram plots energy against what I might call progress of reaction. Let's say reactants to products. Now, if I have, let's say, hydrogen plus oxygen reacting together, maybe they will burn them to form water. Maybe I should actually balance that up. I know that energy is given out as that combustion reaction occurs. And I could say, okay, the difference in energy here represents the delta H of reaction. And because products are more stable than the reactants, then delta H is negative, an exothermic reaction. But I have to actually add in a little bit of energy to get this to occur. And the actual change in energy as the reaction progresses may look something like that, where this initial hump is what we call the activation energy. And the activation energy of a reaction is the minimum amount of energy required in order to get the reaction to go. And as soon as a few molecules of hydrogen and oxygen have reacted to produce water, that has given out energy, and so that energy that's given out is sufficient to get the rest of the reaction going. And what it represents, an activation energy represents a minimum amount of energy necessary to initiate the reaction. And we find that a reaction that occurs easily has a small activation energy. A reaction that occurs with great difficulty, even if it's exothermic and highly exothermic, tends to need a very large activation energy. And what can we do, for example, with a situation where the activation energy is large, but a lot of energy is stored in the material? So, for example, glucose. Glucose has a lot of energy stored in it. And yet, if you took a sample of glucose, it wouldn't spontaneously burst into flames and convert to carbon dioxide and water, even though when it forms carbon dioxide and water, it gives out a large amount of energy. And it doesn't do that because there's a large activation barrier to that process. So that at room temperature, the glucose molecules don't have enough energy to do this transformation. One way around this is if we introduce something we'll call a catalyst, and a catalyst is a material which provides an alternative reaction pathway which has a lower activation barrier. And with a lower activation barrier, then more molecules have the minimum amount of energy required for reaction to occur, and so more molecules can react. And the body actually uses catalysts extensively, because when we do reactions biochemically, then of course we can't, in a body context, we can't use heat we can't use a Bunsen burner to put heat in to get the reaction to occur. So the body has a range of catalysts that do this for us. Now, this was an endothermic reaction. Heat is taken in, and I want to finish off by showing you an exothermic reaction. I'll do it in the fume cupboard because it gives out a bit of heat. I'll just dim the lights. Okay, now what I've got here is a mixture I've got a mixture of iron oxide and aluminium. I'm going to use a bit of a chemical fuse to start it going. Some potassium permanganate, purple stuff. And here we go. So you can see that something's happening. And what you might be able to see is there's molten iron coming out of the bottom of the reaction material. And this is a highly exothermic reaction. We call it the thermite reaction. Termite reaction if you're an Australian, I guess. And a lot of heat's given out. I can feel the heat from here. You can see the molten iron is glowing white hot. I've converted iron oxide and aluminium into aluminium oxide and iron, which is a much more stable arrangement. And I thought that that was a good note on which to finish the lectures. So all the best in your future degrees.